Okay, so we'll try to address now in this session what is the E flag register. So the E flag register is a 32-bit register used in the IA32 architecture. It's part of CPU's internal state and it is automatically updated as a result of most of the operations. One, as a programmer or system designer, don't usually manipulate them directly. It has a big impact on how instructions execute. It contains different types of flags, which we can categorize as status flag, control flags, and system flags. Like if we see the bitwise positions, okay, we can see there are like three kind of categories that you see in front. Like some of the flags are arithmetic flags, which are colored differently, system flags, and then reserved flags. Say like if I talk about bit 0, it contains carry flag. Set This is set when there is a carry out of the most significant bit used in unsigned arithmetic. Like for example, when you add 255 plus 1, this goes to 256. So that means carry flag would be set. At bit number 2, so starting with 0, 1, 2 kind of, it is parity flag. And this is set if the number of ones in the least significant byte of the result is even. Correct. And this is generally used whenever some error checking is actually applied. Then at the fourth bit position, we have auxiliary carry flag. This is set when a carry occurs from bit 3 to bit 4. It is mainly used in binary coded decimal arithmetic. Further, at bit 6, one can see that there is a 0 flag. This will be set like if the result of an operation results to 0. For example, if I compare EX with EX, so both the values are same. So that's why 0 flag is set. At bit number 7, we can see sign flag. This is set if the result is negative and it reflects the most significant bit of the result. At bit number 11, like after 7, so as we are talking about arithmetic only, so it is overflow flag. And this is set when a signed overflow happens. For example, when you are adding two large positive numbers, that results to a negative number because it cannot fit into the particular bit position. Then other set is something called as, say, the system flags or control flags. These are bits that control the execution and they influence how CPU executes the instructions. Like for example, at bit number 8, one can see trap flag. When it is set, it allows single step debugging. The CPU generates a debug exception after every instruction. Then at bit number 9, it is interrupt enable flag. It controls whether maskable hardware interrupts are recognized or not. STI is an instruction which is used to set this interrupt flag, which enables interrupt. And suppose if you want to clear this or disable this flag, then we have to make use of CLI as an instruction, clear it. Right. At bit number 10, like there is something called a direction flag, determines the direction of string operations. And if it is set, the string instructions like MOVS or CMPS will process from high memory to low memory in a decrement manner. So if it is clear, then ultimately the process, they will process normally in terms of incrementing the values. Okay, and there are a few flags which are used by system, bits used in OS and system control. Okay, now these are used mainly by the at the operating system level functions, or probably maybe whenever one is working with advanced processor mode. Say at bit number 12 and bit number 13, it is IO privilege level, IOPL. This defines current privilege level for IO operations, and it is mostly used in protected mode by the operating system. At bit number 14, one can see that is nested task flag. This is used to support task chaining whenever there is a multi-tasking environment used. At bit number 16, we'll see resume flag. It is used for in conjunction with debugging to resume after an exception. Then at bit number 17, it enables, like, it is virtual 8086 mode. So VM, that's why it is called as. So it enables execution of real mode code in a protected mode, virtualized environment. And that's why it is called as virtual 8086 mode. At bit number 18, we will see alignment check, AC. And this helps in checking whether the memory access are aligned or not. There is something called as virtual interrupt flag at bit number 19 and virtual interrupt pending at bit number 20. And both of these are used in virtualization and are managed by the operating system. And lastly, bit number 21, that is ID flag. When set, it allows execution of CPU ID instruction, which is help to retrieve information of a CPU. And there are some bit positions which are reserved, like for example 1, 3, 5, 15. Okay, but like this bit, like for example bit 1 here is always set to 1 and others are undefined or reserved for future use and should not be changed manually, like the positions I'm saying 1, 3, 5, and rest of them probably can have some other impact too. Like as I stated, bit 0 carry flag, it is a status register. Set if carry or borrow occurs, bit 1 is reserved and it is always 1. Bit 2 parity flag. Okay, bit 3 reserved, bit 4 auxiliary carry, 5 reserved, 6 0 flag, 7 sign flag, 8 trap flag, it is control register, control flag, 9 interrupt enable flag, control register or control flag, 10 direction flag, control flag, overflow at bit 11, overflow flag, then 12 13 IOPL, which defines the privilege level. That's why this is to be used by the system. And there are privilege level defined as 0, 1, 2, 3. Bit number 14, NT, nested task, controls nested task chaining. Okay, with multitasking environment. Again, system flag. 15 is reserved. 16, RF, resume execution after debugging exception. 17, virtual mode, enables virtual 8086 mode. 18, AC, alignment check used for alignment fault detection. 19, VIF, virtual interrupt flag, and 20, VIP, virtual interrupt pending. So both of them are used by the virtualization systems. Okay, and like 21, ID, this is ID flag, allows CPU ID instruction or ID information about the CPU can be retrieved. And then rest of the bits from bit number 22 to 31, they are reserved for future use. And this is about the flag register.